że kursor włączyć, tak żeby był widoczny?
Nie wiem.
A jak zmienić pozycję tego zielono-czerwonego? Let's try escape once again, because now we have this in the middle. May I?
Yeah.
Then maybe,
Okay.
and then those should be, yeah, here. Maybe here. This.
Perfect. We still have this one, but
But it's always there, so.
yeah.
But why is it in the middle?
You know what's this one that you cannot more than this.
But this is, I'm more worried about this thing. Maybe I can worry about this.
Okay. Yeah. Okay.
Okay. And so good afternoon, everyone. Today we are having a guest from Germany, Angela Zegarelli. Angela is Italian. She did her PhD and some postdocs in Italy, and then she moved to Germany. She's been working for some years on neutrinos, and that's also the topic of her talk. So be looking forward, and the floor is yours.
Thanks a lot for the introduction. So nice to meet you, everyone. And it's really a pleasure for me to be here to explain something very different from what we do. So today we talk about neutron astronomy with the IceCube Neutrino telescope. So I'd like to start with this citation that the physicist Markov did more than 60 years ago. That's the idea of how doing neutrino physics, and in particular in our case, neutron storm. So he said we propose setting up apparatus in an underground lake or deep in the ocean in order to separate charge particle directions by channel contribution. So the first difference with respect to neutron astronomy, with respect to the astronomy in general, is that for neutrinos we go underground lake or deep, or in the case of IceCube, as we see, under the ice. So it's a very different way of doing astronomy with respect to what you're used to, because you use telescopes on top of mountains, satellites, so it's a very different kind of astronomy. And I want to highlight the main characteristics that will be clear during the talk. That is, we go underground, as I said, and we use the so-called Cherenkov radiation to detect these neutrinos. And I'll explain you later what it means. So after 60 years from this, we have 3 operating Cherenkov neutrino telescopes around the world doing neutrino astronomy. There are some other proposals for the future, but in this slide you see only the telescopes that right now are taking data. So we have in the northern hemisphere the so-called cubic-kilometer neutrino telescope that is under construction, even though it's taking data right now with partial detector configurations, and the goal is to achieve more than 1 cubic kilometer of data under the data you can see. And then there is by CalGVD, another telescope taking data that is under construction, which in this case the goal is to achieve 1 cubic kilometer volume, and this is under the Lake Baikal in Russia. And then there is IceCube, where I'm full member of the IceCube collaboration right now. This is located under the ice. It's at the South Pole. 1 cubic kilometer with instrumented volume, taking data in its full detector configuration since 2011. So we have these telescopes around the world, and the focus of this talk will be the IceCube Neutrino telescopes I'm working right now. So let me present you what IceCube Neutrino Observatory is. So I said it's located at the South Pole. So we have this instrument deep in the ice between 1.5 and 2.5 kilometers under the ice. So basically the instrument is equipped with all these lines that we call streams. And in these streams, there are 60 digital optical modules that are these guys here, equipped with photomultipliers that are able to detect the Cherenkov light that I mentioned before. And I'll explain you in a while what the Cherenkov light is and how we do this. So with this detector, coming back to the slide before, with this detector, we are sensitive to GV sub TV, to TV, PV energy range. So we we do neutrino astronomy until very high energy. Consider that the EB is 10 to 13, 10 to 15 electron volt. So data is collected here at the South Pole and then is sent to the north in Madison in the US through satellites. Okay, so with these photomultipliers in digital optical modules that we see in these strings, we collect this light, this channel of light, as I said, and we're able to infer which was the direction of the neutrinos and also the energy with a precision of the nanoseconds. So let me explain you better. So for example, this is an animation of the DOM, of the digital optical module that we have in the strings. We have 60 of those in one single string, and we have more than 100 strings in the eyes, 125 strings. So the detector looks like this, and how does it work? So here, for example, you can see this animation, the simulation of an event, a typical event. The arrow is the neutrino coming, then at this point the neutrino interacts in the eyes, and there is the production of other particles that produce Cherenkov radiation. That is this cone of light that you can see here. So basically what happens is that the neutrino interacts in the eyes, produces other particles. These particles are very energetic. They have a velocity that is higher than the velocity of the light in the medium, is C over n, where n is the refractive index of the eyes, for example, in this case. So the velocity of the particle, if exceeds this velocity, around 0.8, the velocity of the light in vacuum, there is the production of the so-called Cherenkov flow, so this cone of light optical band. And thanks to the photomultipliers in these digital optical modules, we detect this light, basically. And from this, we are able to infer which was the direction of the neutrino and also the energy, because these blobs here represent how much light is hit in the photomultiplier. So basically, the bigger they are, the higher the energy. So in this slide, you see at the left a schematic picture of the animation shown before. There's something that I want to point out is that actually we don't detect directly the neutrino. As I said before, we detect the neutrino interacts in the eyes, and then there is some other particles that are produced. And these particles travel at the speed that is higher than the speed of light in the medium, and these particles produce this Cherenkov light that we detect with those. So basically, we detect, for example, in the case of this specific interaction channel, I don't want to go into details on neutrino physics, but in the case of this specific neutrino channel, we detect the muon, so not directly neutrino. But from the direction and the energy of this muon, we can infer which was the direction of energy of the incoming neutrino. But there is something to know here, because actually there is, after the interaction, there is a given kinematic angle between the particle and the incoming neutrino, but this kinematic angle is lower for higher energies. So this means that for very energetic neutrinos, that are those interesting in neutrino astronomy, this angle is low, so we can reconstruct quite well which was the original direction of the neutrino. This is one example of the signatures that we have in our detector. This is the so-called track-like events. But we can have also so-called cascade events or so-called showers, depending on other neutrino flavors and neutrino diffraction channels. So we have these two main channels, track and cascades. And they have different characteristics, let's say, because in the first case, we are able to reconstruct quite well the direction, because you see, it's easy, let's say, to reconstruct which was the direction of the incoming neutrino, because the track is very long inside the detector, can also escape the detector itself, detector volume, if the energy is very high. While in this case, in the case of shower channels, in this case, we have a blob of light, let's say, left inside the detector. So it's difficult to reconstruct well the vertex, interaction vertex of neutrino, so reconstruct well which was the direction of this neutrino. But the trade-off of this is that for cascades, we can reconstruct well which is the energy of the event, because most of the light is left within the detector volume, while in this case, not. Because if the track is very energetic, this track can also leave the detector, and if there is some other lights that we are losing, because we don't have any more strings in the optical models. So in this case, when we detect the energy, it's a kind of lower limit of the real energy of the neutrino. And you can find here which are the characteristics. So in the case of tracks, we say neutrino astronomy, we consider this a good angular resolution, for example, 5.5 degrees for energies above 10 TeV. It's very different from other astronomical studies, while the energy resolution is poorer than the cascade channel, where the angular resolution is pretty good. Okay, this is just to give you an overview of the event topologies that we observe. And here you can see an animation of a shower event with an energy of PV. So you can see this is slow down for clarity, of course. And you can see that in this case, we have this blob of light. So it's difficult to actually understand clearly with a small uncertainty, which was the direction of the incoming neutrino generating this. And this is also another example here for even more energetic event. These are really real detected events by IceCube, not simulations anymore. While in the case of the track, this is a real track. It's similar to what I've shown at the beginning of the simulation of the Sharepov cone. So after a while, there is the development of the entire track, and so you can see that actually it's easier to understand which is the direction. Also, it comes from somewhere here. Okay. So this is the way we detect neutrinos, and actually I'm talking about neutron astronomy in this seminar, but IceCube can do plenty of science. This is an octopus diagram that we usually show to highlight, to summarize all the science cases that we can cover with IceCube, even though the major science goals of IceCube is neutrino physics, in particular neutrino oscillations, that is not part of this seminar today. We focus on astrophysics, and in particular, I highlighted these three boxes: cosmic accelerators, multimessenger astronomy, and neutrino astronomy. I imagine that for you this is something very new. So I'd like to explain you in the next slides what multimessenger astronomy is, why neutrinos can play a role in this field, and so yes, with the telescope, and what are cosmic accelerators in the sky. So let me start this new chapter, let's say, of this presentation with the spectrum of cosmic rays. Cosmic rays are charged particles that we detect coming from different locations in the sky, different energies. So you see the energy flux as a function of energy here. This is the most energetic events detected at CERN in the NIV, so interstellar circuit. And you see that actually in nature exists also particles much more energetic, up to 10 to 20 electron volts. And if you, in this case, we have, of course, we have the number of particles is quite low, is 1 particle for every square kilometer. And if we zoom in this region, I don't want to go into the details of the spectral features, but I want to highlight that, for example, if you go to this very extreme high energies, to 10 to 20 electron volts, we know that sources in accelerating those cosmic rays till these extreme high energies need to be extragalactic, because events so energetic cannot be produced in sources inside our galaxy, because they are so energetic that if you consider also the magnetic field in our galaxy, they cannot be confined inside the dimension of our galaxy. So of course, we know that extragalactic sources need to produce these cosmic rays, but we don't know clearly which are those. So let me explain why these cosmic rays are related to neutrinos. So let's consider an astrophysical source in the sky. In astrophysical source in the sky, it can happen that we have protons, so hadrons, accelerating near the source engine, and then can interact with other matter surrounding the engine or photons. And from this interaction, we have the production of other particles called pions. And from the charged pions, from the decay of charged pions, we have photons. And from the decay, neutral pions. And from the decay of charged pions, we have neutrinos. So if you see this channel, basically, this box, you see that at the same time, from the acceleration of cosmic rays through PP of P-gamma interactions, we have photons and also neutrinos. And these neutrinos have more or less, on average, 5% of the energy incoming from. So it's clear that all these messengers can be related to each other. And there are also some other astrophysical systems, for example, binary neutron-star mergers that can produce also gravitational waves. So this is the so-called multi-messenger feature. So basically, we have sources in the sky that can accelerate cosmic rays. If these accelerate cosmic rays, of course, they produce also gamma rays and neutrinos, and they can produce also GWs. And that's why there is a big effort in the community to actually collect information from all these cosmic messengers to try to combine them, see if it's possible to have combined observations and then to characterize those sources. And of course, IceCube aims to detect those neutrinos. Okay, in the universe, we have a lot of potential cosmic accelerators. In this slide, I just show you some examples. That can be some galaxy, extragalactic nuclei. We can have also neutrinos from our galaxy at energy a bit below the extragalactic ones, gamma ray bursts, supernova explosions, static disruption events. And this is just a small list of all the sources that can, in principle, accelerate cosmic rays and produce those neutrinos. And I want to also explain why neutrinos are considered ideal messengers among all the others that I mentioned before. And let me compare the neutrinos to the other messengers. So if we see on cosmic rays, when they are accelerated at source, then there are magnetic fields in the universe, so they are deflected. And so when we detect them at the Earth, we cannot actually reconstruct which was the direction where they were produced. And also there is also the uncertainty of modeling of magnetic fields in the universe. This is not the case of gamma rays, that of course they are neutral particles, so they can trace sources. But there is the problem, let's say that at very high energy and TV energy, gamma rays interact with photons of the extragalactic background light, so their flux is suppressed. For neutrinos, that's not the case, because neutrinos are particles that interact electrical neutrons, stable, with interacting particles, so they are neither deflected and absorbed. So if, for example, we detect an astrophysical neutrino, we reconstruct well the direction of this neutrino, we can actually come back to the direction in the sky, in the universe, where this neutrino was created. And we can, in principle, search for electromagnetic counterflows. And there is also other positive aspects of neutrinos with respect to gamma rays, because, okay, if we consider gamma rays not at extreme energies, without absorption, they can trace the direction, but gamma rays can be produced also in sources where only leptonic processes are working, radiation processes like inverse Compton, Bremsstrahlung, this kind of stuff. Why neutrinos to be produced need to require cosmic ray acceleration. So this means that if we detect an astrophysical neutrino and we are able to associate this astrophysical neutrino to a source in the sky, this means that this source works as a cosmic ray accelerator. So in the search engine, there is some cosmic ray acceleration. And you can see these also in this plot, showing the distance in megaparsec compared to some references to galactic center, nearest galaxy, and so on. As a function of the energy that corresponds to some wavelengths, of course. So in this plot, you see from radio to gamma rays, and this is the gamma ray horizon because of the absorption with extragalactic background light. This region is opaque to gamma rays, but is transparent to neutrinos and GWs. Okay. So far, I highlighted all the positive aspects of neutrinos, but actually it's very difficult to detect them. We have a huge background in our detectors. And let me explain how we reject this background and which kind of background we have. So our background is the following. Cosmic rays arrive, interacts in the Earth atmosphere and produce a lot of neutrinos and muons. And these neutrinos and muons can reach our detector. And of course, atmospheric neutrinos can interact with nuclei in the ice and can produce tracks and shower channels, signatures that I showed. And also this atmospheric muon can traverse the detector and produce the track signature, but it's background, not signal. So how do we deal with this? Actually, these are quite huge background. For example, for atmospheric muons, we have 3,000 events per second. And for atmospheric neutrino, 1 event every a few minutes, let's say. And astrophysical neutrinos are much, much lower filter here. So how do we deal with this background? So let me divide the sky in upgoing and downgoing. This is the IceCube detector. This is the so-called upgoing sky detector, and this is the downgoing one. So in this plot, you see the rate of events, atmospheric neutrinos and muons as a function of the cosine of the zenith angle. This corresponds to the upgoing sky. This is the northern sky for the detector, and this is the downgoing one, the southern sky. You see that from the southern sky, we have a lot of background of atmospheric muons, of course, because of interaction cosmic phase with the Earth's atmosphere. But this is reduced. This actually, we don't have any more at all these atmospheric muon flux if we go to the upgoing sky. So if we select all events coming from this direction, we avoid all this background flux, those atmospheric muons cannot traverse the Earth. So in this case, we have only the atmospheric neutrino flux that we cannot avoid, because neutrinos, because of their characteristics, reach this effect. So this is how we do for the upgoing sky. But what about the downgoing one? So in this region of the sky, we cannot avoid atmospheric flux, but we can in some way reduce it. And how is it possible to control? So basically, I told you before that the muons produced in the atmosphere, in this case, that we see on these events here, can traverse the detector. So muons create a signature like this, a track-like event like this. So in principle, this track-like event can be produced also by a neutrino interacting a bit outside of the detector volume. And we see just the secondary particles traversing our detector. So if we select only so-called static events, so events, track-like events, where we clearly identify the neutrino interaction point inside the detector, at least we are sure that this is not a muon background event, because if it was a muon background event, it was generated in the atmosphere, so it cannot start inside the detector. So at this point, we can reduce this muon background event, even though, okay, we have to distinguish this neutrino if it is background atmospheric neutrino or still. But this helps, by the way, reducing this atmospheric muon background. And also, actually, I want to add that this atmospheric muon flux is lower if we go deeper. And that's why we put the strings of the IceCube detector between 1.5 and 2.5 kilometers. And for example, ChemTreeNet in the northern hemisphere under the sea is putting strings between 2 till 3.5 kilometers. Because if you go deeper, you also reduce even more in the downgoing sky of the detector this flux of atmospheric muons. Okay. But I mentioned that we cannot avoid atmospheric neutrinos. But for astronomical studies, let's say, there is something that helps us. Because you see the neutrino spectrum at the Earth is the following. And the green one represents the atmospheric neutrino flux, and the red one, the astrophysical neutrino flux that we expect from calculations from cosmic ray information. And if we zoom in this region, you see that above 100 TeV, that is actually the region we are more interested in for neutrino astronomy, the astrophysical neutrino flux stands out over the atmospheric one. So at these energies, actually, we expect more astrophysical neutrinos than atmospheric ones. So this helps us a bit. And so after discussing how we detect these neutrinos, how we eject the ground, I'd like to also mention how we search for these neutrino sources. So we have two possible ways. We look at possible clustering of the sky. For example, we have some catalog sources that we can consider, and we see from this direction of the sky there is a neutrino excess in data with respect to the ground, reflecting the statistics. Or, for example, for transient sources, we can see if there is a possible flare in neutrinos. And this is something very interesting, for example, for the multimessenger. Okay, so after this long introduction about neutrino astronomy, why it's interesting for us, I like to show you some key results of IceCube achieved since it started in data in 2011. And so I showed these results in a timeline since since IceCube was completed till now. So the first detection, the first discovery was 2 years after IceCube was completed in 2013. There was the first detection of astrophysical neutrinos at TV energies. So this is considered the birth of the anti-neutron astronomy. Of course, this is not the first detection of astrophysical neutrinos in the sense that we have also solar neutrinos. We have neutrinos from the supernova 1978, but in this case, the energies were lower at mid energies. While here we have several order of magnitudes higher. And this is the map, the first map of those neutrinos. You can see how they are located in the sky. This is the excess with respect to the ground. But the point is that there was this flux of neutrinos discovered, astrophysical neutrinos without significance. But these neutrinos were not associated to any known electromagnetic counterpart or known sources. So the origin of the neutrinos was totally unknown. And over the years, IceCube has collected a lot of data, increasing the significance. For example, now the significance of this detection is above 6 sigma. And but still, it was hard to, let's say, explain with some astrophysical sources in the sky this flux that you see plotted here in this plot showing the energy density as a function of energy, together to gamma rays from Fermi-Lab satellites and ultra-high energy cosmic rays, those cosmic rays that need to come from extragalactic sources that explain at the beginning. And it's interesting to point out here that actually it seems that there is a similar energy density in the universe in gamma rays, neutrinos, and cosmic rays. So maybe there is a need of a common origin between these cosmic messengers. And this makes sense actually, because I showed you at the beginning that to produce neutrinos, we require cosmic ray accelerations, and there is at the same time also gamma ray production. So the idea of multimessenger astronomy is actually to explain these diffuse fluxes of multiple messengers. And I like just to mention that one recent result of the IceCube collaboration about this diffuse flux, because we are detecting this diffuse flux since 13 years. And it has been always breastfeeding like the power law. Now there is something new that is coming out, so a new feature emerging, because since there is a new spectral features around 30 TeV, and so maybe it can mean that we have several population sources contributing to this flux. Maybe it's related to the way cosmic rays are accelerated, something that is very new. We published this 1 month ago. So something that really needs to be explained. But anyway, it's the first time that we find this kind of break in the diffuse flux of astrophysical neutrinos. And this can, of course, help us in constraining the population of sources that contribute to this flux that, again, we still need to totally explain. So, okay, we know, so I showed you that we have this diffuse flux of high-energy neutrinos discovered, so we know that astrophysical neutrinos of TV energies exist, but what are the sources? I spoiled you that we still don't know, but we have some association and indication found by IceCube, and I want to show you these indications. The first one comes from the so-called IceCube real-time program. What is this? So basically, in 2016, IceCube started sending the neutrino alerts with a latency of on average 30 seconds to the community. So if we have some filters able to identify interesting neutrinos with high probability of being astrophysical, and we send some alerts to the community so that other telescopes, gamma rays, optical, other wavelengths, whatever, can follow up this neutrino alert and check if in this direction up in the sky there is something, an electromagnetic pulse. And we send these alerts in both channels, tracks, and cascades. And this is the rate of these alerts. So this is basically the schema, for example, for track alerts. We send this first reconstruction with a latency of 30 seconds on average, typically within 1 minute. And then we also send a refined reconstruction a few hours later, because that's in the meanwhile, okay, telescope has started following up, for example, our neutral Earth, but a few hours later we can refine our reconstruction so that we provide a more precise reconstruction of the neutral Earth that we already sent out a few hours before. And the goal again is to alert the multimessenger community about maybe possible interest in the sky, and so other telescopes can decide if following up these neutral Earths. And thanks to this program, there was the first identification of a possible neutrino source in 2017, just a year after the launch of the real-time program. In this case, there was this source is the base at excess of 6.56, active galactic nuclei with a relativistic jets pointing towards us. So this was the neutrino event with an energy between 250 to 300 TeV, and probability of astrophysical origin around 16%. The correlation of the significance was 3 sigma, not so evident, but 5 sigma discovery, but it was still interesting. This is the best fit direction of the IceCube neutrino provided by IceCube with the uncertainties 50 and 90%. And I don't know if you can see well, but this orange red spot represents the gamma ray signal detected by Fermi-Lab that follow up the neutral Earth together with energy. And so they discovered that actually at the moment of the neutral Earth and at the same location of it, there was a flaring laser in gamma. So this is how this alert that we sent out looks like. So you can see this is a clear track. And yeah, after having detected these 30 seconds, within 30 seconds, we were able to alert the community about the presence of this possible interesting events. And I like showing also this map. So here you see the start of the real-time program. This is the map of the Fermi-Lab satellite, and this shows the gamma ray intensity. So this is the start of the IceCube real-time program. Then I start the animation. So this is how the gamma ray intensity evolves, and sometimes you see some spots corresponding to the IceCube track alerts that we send. And at a certain point in September 2027, corresponding to this alert I mentioned so far, yeah, there is a zoom in this region of the sky, and there is the flare in gamma detected by Fermi. And here you see it's just to give you an idea of the intense follow-up detections of these alerts after the IceCube notice. So there was an intense follow-up activities, even months later the alert. This allows to characterize deeply the source. So despite of the association with this neutrino, this kind of study allows to deeply investigate, deeply observe and characterize that source. And so it was very important also for the astronomical community to understand how this blazar works. So this is a great example. This was a great success of multimessenger astronomy because it demonstrates that actually, if we promptly share information to the other astronomical community and so to the multimessenger community, we can approach something important. For example, in this case, there was the first identification of a possible cosmic environment acceleration. And just to let you know, after that, thanks to offline analysis, it was possible to identify another neutrino flare corresponding to the same direction in the sky of 3.5 sigma. So there was an excess corresponding to this data offline data a few years before. So post the neutrino producer. Okay, so this was the first association. Let's go to 2022, when IceCube identified another source possibly producing neutrinos with a significance of 4 sigma this time. This is the Seeker Galaxy NGC-1068, so a steady source, not a transient flaring laser anymore. This was a result of an offline analysis, so it was not part of this real-time program. So people analyzed data collected over the years through specific, they performed specific test statistics studies. So it was a time integrated neutrino search using a likelihood-based analysis. And it was possible to identify this neutrino spot with a significance again of around 4 sigma that is consistent with the position of NGC 68, so this here, the secret galaxy type 2. And you can see in this plot the excess of data with respect to the distance to the galaxy. This is the background, and this is the. So in this case, it was an excess of around 8 events from this direction in this sky. And so at this point, we can, of course, ask the question, can TXS and NGC contribute to the diffuse flux detected by IceCube? The answer is only partially. They contribute few percent at most. So this is the diffuse flux of IceCube. This is the contribution of NGC 68. This is the contribution of TXS, 506 plus 56. They contribute at different energies, but still, there is a lot, there is a big gap from the surface. Okay, so after that, there were also some other analyses started in IceCube, but there was an increasing interest in X-ray agents. Why? This comes from NGC 68 again, because actually, if we see this plot, so this is the energy density as a function of energy, this is IceCube data, neutrino. Since this source is associated to these TV neutrinos towards PV, we expect also TV gamma rays associated to this source, but we are not observing TV gamma rays. And here, these TV gamma rays are not observed by the extragalactic granular because the source is very close, 14.4 megawatts. So at this distance, we don't expect absorption because of the extragalactic granular. So this means that something else is happening. So we see just GV gamma rays, we have some rays here, but we have also X-rays observed corresponding to the source. So this was the hypothesis developed by theoreticians, and also I think this is the most plausible one, that the neutrino emission region is happens in a region that is optically thick gamma rays. So the so-called corona region, and also the black hole, where dense matter radiation now scatters gamma rays to X-rays. And so that's why we see X-rays here. And that's why now in IceCube we are doing a lot of searches, searching for correlations between neutrinos and X-ray AGS. So we have a lot of searches ongoing, where I put here some recent publications, and we found some correlations at 3 sigma. So there is maybe an emerging picture of gamma ray obscured AGS that can produce neutrinos. And I put here the figures of some of these galaxies. These are all super galaxies that produce these 3 sigma correlations. So of course, in this analysis, a lot of more sources have been considered, because there were several catalogs considered, but all the other sources provided a sigma that was lower than 3. So not considered. We cannot consider it an association with it. And from one of our recent papers, I took these plots that compares again the IceCube diffuse flux, NGC 68, the obtained flux, and also these 3 sources, the one that I showed here, that contribute, for which we find an association around 3 sigma. These are the sources. And the most promising one after NGC 68, that again is the only one with 4 sigma, is this one, 7469, C1 galaxy. And this flux is actually dominated by 2 events that were also sent out as neutrino alerts in the past by the IceCube real-time program. And indeed, there was a publication that highlighted this, so that found this possible association between these IceCube real-time alerts and this source. Okay, and lastly, 3 years ago, there was the first identification of neutrinos from the Milky Way. So we have also neutrinos from our galaxy. So far we have some jets, and now Milky Way. This analysis used 10 years of data, and without going into details of this analysis, but it was possible actually to prove that more or less 10% of the diffuse flux of neutrinos, the one I'm talking about since the beginning, can be explained by our from the galactic plane. So you see, this is the map, the neutron map. This is the galactic. And this happens because cosmic rays propagate through the galaxy and interacts with photons and matter. Okay, so this is the significance of this correlation was 4.5 sigma. But now we are improving our data sets, our extraction, etc. And there are some analyses still not published, but we have some proceedings published after conferences that push the significance of this association with the neutrinos from the Milky Way as far as. Okay, so I gave you an overview of which are the sources that contribute to this diffuse flux of neutrinos, and in particular in this plot, I show the last diffuse fluxes by IceCube, the contribution by the galaxy, the contribution by energy 1068, that are the most promising sources. So we are in this situation in which we have associated 10% of the flux with the galaxy, with the Milky Way, 1% with some blazars, but what about the remaining? We don't know, we still need to understand. And I'm pretty sure that an important role can be played by the IceCube Neutrino program. So let's come back to what I mentioned at the beginning of the key results of IceCube. I talked about the IceCube Neutrino program that allows to identify the great excess of 556 as the first possible cosmic pairs reflux. We are improving the IceCube real-time program in the last years. And to explain you the improvements, I want to also mention that a few years ago, IceCube published the catalog of all the alerts released so far. So the public catalog. The difference with respect to, of course, we are publicly releasing alerts in real time since 2017. So what's the point here is that IceCube reprocessed all the events since the beginning of the detector. So basically, in this catalog, you see also all the alerts that would have triggered if the real-time program was active before 2017. So in this catalog, you see all the alerts after 2016, 16 and till 2029. And this was used a lot within the multimessenger community for a lot of studies to associate sources to tidal disruption events and other sources. But now we are releasing a new catalog, and this can make the difference because all the association can be checked again. Why? Because in September 2024, we applied the real-time a big change. We have updated the reconstruction algorithms that we used to send the refined reconstruction a few hours later, the first preliminary reconstruction. So now we have a big improvement in the localization uncertainty around the bed speeds that I show you in this slide. This comes from the catalog that we're building. So we are processing all the old catalog using this new reconstruction algorithms that are in place since September 2024. So now we have all these events since 2011 in process with these events. And you can see here the comparison, the ratio between the old area and the new one. This is logarithm of this ratio, and for the 50 and 90% in blue and orange, respectively, containment around the speed. And on the median of this is close to 5. So we are shrinking basically the area of a factor around 5. So we are improving quite a lot the precision of our reconstructions with respect to this. And this is very, very important to associate possible electromagnetic counterparts to neutrinos. To give an idea, for example, I show in this map IceCube for a portion of the catalog that we published, which were the old best direction and the manifold and contours, in this case the rectangular error box, the rectangular error box represents these manifolds and contours. And this is the corresponding map in IceCube 2 in the new catalog. So you see how big the improvement is. So it's very important to associate possible electromagnetic contours. Of course, with this new catalog and new reconstruction, so we checked if the sources associated in real time so far are still inside the new contours. And of course, we checked TXS 56 plus 56. That was the first source identified. In red, you see all the reconstruction. So this is the uncertainties of 50% and 90%. And in blue, the new reconstruction. You see this is the position of the blazar is still inside the blue. So, okay, still possible neutrino source. Then we checked also MGC 7469, because I told you that this is one of the sources giving the 3 sigma association, but the flux was dominated by the 2 neutrino alerts that we also sent in the past, in 22 and 23. These were the reconstruction in IceCube 1, and this the reconstruction in IceCube 2. So the activity reconstruction locates the source still inside the contours. It's not the case for total disruption events. We have a few cases of total disruption events, these ones that in the past were associated maybe to some neutrinos, even though these, for example, in a few cases, the location of these total disruption events were maybe at the border of the contours, let's say, of the IceCube. And these associations were found, these possible associations, let's say, were found with the optical and ultraviolet, the peak of the optical and ultraviolet signal 100 days after neutrinos. But now, if you see the blue contours, you see that these sources are outside the new uncertainties. So this means that in particular for these 3Ds, we can constrain the whole population of 3Ds, but in particular for these 2 3Ds, these associations are disfavored. So this is something that we have to keep in mind. And lastly, another very important improvement in the real-time program is that since January of this year, we are releasing multi-orbit probability maps. So basically, before the January, we were just releasing this rectangular error box that I showed in the maps before. And now we have started releasing this fixed file containing for each pixel, which is the actual probability that the direction that the neutrino comes from that pixel in the sky, the direction in the sky. This is true from real-time alerts since January 2026, but actually will make available these probability maps for all the alerts in IceCube 2 when this will be public in the next months. The paper is in preparation and inside the evaluation. And this is very important because these does have different level of improvement, of course in online, because every telescope, if for example you want to follow up a specific neutrino alert, it can decide its own strategy, let's say. Because for example, if you go back to this map, you can say, okay, I wanna just check if there is something within 50%, even lower. So you can actually check which was the actual, you cannot see, but this is the 50% containment, this is the 90% containment, but you can play with this map. So you can really decide your strategy. And this was not possible before, let's say, or maybe it was possible, but in less precise way. And also for offline analysis, of course, because when we release the IceCube catalog, these multi-orbit probability maps, it's possible to build more precise, likelihood-based analysis and also accurate correlation with currents. And this is the last slide of my presentation, giving you an idea of what is possible to do these kind of studies. So we have a neutrino alert, then the other telescopes can follow up this alert, as I'm saying since a lot of slides right now. And I want to stress that in this kind of studies, it's very important to define and optimize a good strategy between neutrino observatories and electromagnetic ones. Because in neutrinos we have profile visibility, continuous, we have a full duty cycle, so we don't have to decide where looking, in which direction we have to look in the sky, for example, optical telescopes and other telescopes. So we basically have every time access to data from all the universe. That's not the case for electromagnetic instruments. And so since there are several transient sources that can potentially produce these neutrinos, it's very important to optimize the strategies between neutrino telescopes and electromagnetic observatories. And I have no time to discuss this here, but I also work on, I investigate this for a specific class of sources that is called collapsed supernovae hosting relativistic jets, basically faint debris from which we can observe gamma rays because they are shot inside the stellar envelope. If you are interested, we can talk later about this. So this is my last slide with the take-home message. I showed you which are the key associations of IceCube so far. Still, we have the main question of which are the sources producing these neutrinos, because we have only a few associations so far, and we have updated this by some analysis with no associations, but we can explain for just 10% or a bit more than this one. So there is a lot to understand, and in these fields, the IceCube Neutrino program plays an important role, and I hope it will play. It will be even better in the next year since we are introducing these improvements in our real-time program, in which I'm deeply involved. So what's next? Stay tuned. I hope that this was a bit interesting for you, even though it's very different kind of astronomy, let's say. And thank you for the attention.
Thank you, Angela, for a very, very nice overview. Do you have any questions or comments?
So what is the timeline for IceCube?
Depends on the review inside the collaboration. Let's say the goal is within this year. Yeah, depends on because there are very long review stages inside these two collaborations. Yeah, the paper draft is ready and we submit a review, and so we hope.
Okay.
So, as soon as possible.
So to follow on this, so is the number of sources also changing in the second catalog?
Yeah, we have
same sources.
the same sources plus the new one. So we have 300, around 400 sources. Neutrinos, yeah, since 2011 to now.
I have another one. So in the public alerts of neutrino, the alerts are classified by gold, bronze, and silver.
Yes.
So like, what is the difference between?
Yeah, the gold stream is for alerts with a higher probability of being astrophysical. On average, the probability of being astrophysical is around 50% on average, but there are also some events with even higher probability. For the bronze stream, the probability is a bit lower, so the astrophysical purity, let's say, is worse. So the probability to have background is higher. So we have that in this case for the bronze stream, the astrophysical purity is around 15%. So that's the difference. So in the case of the gold stream, you are more, let's say, it's more probable that they are astrophysical with respect to the bronze one. But this doesn't imply that a bronze alert cannot have a high probability of being astrophysical, because it depends. This probability of being astrophysical is something that is calculated afterwards. So we have some filters that, depending on the characteristics of the alerts, classify the event as bronze or gold, and afterwards there is the estimation of the astrophysical probability. So it can also be that, for example, bronze alerts you are quite reasonable in our astrophysical.
So last year there was a recent circular regarding like multiple galactic events after first neutrino with the associated gravitational event. So I don't know if you are aware of it. I am
Which GW?
yeah, there was a circular regarding electromagnetic counterpart. like neutrino counterpart understand the. I'm not sure, like, I just wanted to ask, like, if you have any comments regarding that, or like, if there
If there was, it was nothing very significant, of course, because yeah, but maybe it was a circular specific to follow up GW alerts that we perform. That I didn't
Yeah,
mention.
yeah.
Okay, yeah. No, because we have some specific programs to follow up every GW alerts. And so maybe there was a key value that was
Yeah,
one, but still not significant. Yeah, what can be first? Because I didn't mention, but we have this, we follow up every GW alert. Every time there is a new GW, we follow up this alert. So we then publish circulars with the results.
No? Anyone on the Zoom?
I can see any question.
Okay, if not, let's thank
Thank
speaker
you.
again. And next week, there will be the last seminar of the semester, and that'll be about doing coffee. So yeah, so the physics behind a good espresso, maybe with tasting. So you should come as well. You see,
Yeah,
as an
that's
Italian.
it.
So
Yes.
And we think